The topic I am going to discuss is higher order derivatives. We consider an example. Let y be equal to sine x. Differentiate both sides. What we get is d by dx of y is equal to d by dx of sine x. That is dy by dx is equal to differentiation of sine x is cos x. If we now again differentiate this with respect to x, what we get is we will get d by dx of dy by dx. We are differentiating dy by dx with respect to x. So d by dx of dy by dx will be equal to d by dx of cos x. And this is generally written as this is d2 by dx square. That is second order derivative of y with respect to x. Second order derivative of y with respect to x. This is denoted by d2y by dx square, and this is equal to d by dx of cos x is minus sine x. So this is the first order derivative of sine x, and this is the second order derivative of sine x. Y is sine x. This is the second order derivative of sine x. And if we differentiate this again with respect to x, what we get is d by dx of, we are differentiating this, so this is d2y by dx square. This is equal to minus d by dx of sine x. And this is written as d3 by dx cube. Third order derivative with respect to x of y. This is equal to, now d by dx of sine x is cos x. This is minus cos x, and so on. If I differentiate it again with respect to x, we will have d4 by dx4 of y is differential of cos is minus sine. So this will be sine x, and you can obtain higher order derivatives. Now second thing is notation. There are 3-4 notations which are generally used. I will tell you all the notations here and then use them. Now first is, if the function is y, then its first order derivative is dy by dx. Its second order derivative is d2y by dx square. Third order derivative is d3y by dx cube. Fourth order derivative is d4y by dx 4, and so on. And second is, if the function is y, its first derivative can also be denoted by y1, second order derivative by y2, third order derivative by y3, fourth order derivative by y4, and so on. Order of the derivative is written as a subscript. Second order derivative, 2 is the subscript. Third order derivative, 3 is written in the subscript. Fourth order derivative, this is written here. And next is, if the function is y, we can also denote the derivative by y dash. Y double dash, second order derivative. Third order derivative is y triple dash. And fourth order derivative can also be denoted by y4, and so on. Order of the derivative is written in terms of Roman numerals. If the function is denoted by, say, fx, then first order derivative will be f dash x. Second order derivative will be f double dash x. Third order derivative will be f triple dash x. And fourth order derivative will be denoted by this, and so on. If we use this notation, it will be f, f1, f2, f3, F4 and so on. So these are the four popular notations that are generally used. We will use any one of these. Now I take up some questions based on higher order derivatives. First of all, I will take a question based on explicit functions, then for implicit functions, then for parametric functions, and then for logarithmic differentiation. Two questions of each form, and then we will move on to the next chapter. Now first is, we are given this function and we have to find its second order derivative. So what we do is we differentiate both sides of this by x. So what we get is dy by dx is equal to, now differentiation of log is 1 upon x plus under root x square plus a square into differentiation of inner function d by dx of x plus under root x square plus a square. This is log of fx. So differentiation will be 1 by fx, and never forget to write the differentiation of the inner function, that is f dash x. So this is equal to 1 upon x plus under root x square plus a square into d by dx of x is 1 plus, now d by dx of x square plus a square to the power of half. So this will be half x square plus a square to the power of half minus 1 is minus half into d by dx of inner function, that is x square plus a square into d by dx of inner function. This will be differentiation of x is 1. This is x square plus a square to the power of half. So differentiation will be half x square plus a square to the power of minus half, and instead of x we have x square plus a square. So we must take the differentiation of the inner function. So this is equal to 1 upon x plus under the root x square plus a square whole into 1 plus 1 by 2 x square plus a square to the power of minus half is under root of x square plus a square minus, so in the denominator, into d by dx of x square plus a square. D by dx of x square plus a square will be 2x. This 2 cancels with this. This is equal to 1 upon x plus under root x square plus a square whole into, now this is the LCM, x square plus a square, and this will be x square plus a square plus x. Now this cancels with this, and we are left with 1 upon under root x square plus a square. Now we have to find the second order derivative. So we differentiate this again with respect to x. Differentiating both sides with respect to x. What we get is d2y by dx square is equal to d by dx of x square plus a square to the power of minus half. So this is equal to minus half into x square plus a square whole to the power of minus 3 by 2 into d by dx of inner function, that is x square plus a square, and this is equal to minus half into x square plus a square to the power of minus 3 by 2 into differentiation of this will be 2x. Now this 2 cancels with this, and we are left with minus x upon x square plus a square to the power of 3 by 2. This is 1 upon x square plus a square to the power of 3 by 2, which can be written as x square plus a square whole into under root x square plus a square. And this is the required answer. This is the answer. Now in this question we are given y is equal to x cube log x, and we have to find the fourth order derivative of this. So what we do is we differentiate both sides of this with respect to x. So what we get is dy by dx is equal to first function into differentiation of log x. Differentiation of log x is 1 by x plus second function log x into differentiation of first is 3x square. So what we get is x square plus 3x square log x. 3x square log x. We do not take x square outside. We prefer these terms as it is. So what we get is, on differentiating, t2y by dx square is equal to 2x plus 3 into first function differentiation of second. Differentiation of log x is 1 by x plus second function log x into differentiation of first is 2x. So this is equal to 2x plus these two cancels and we are left with x. So 3x plus 3 2s are 6. 6x log x. 6x log x. This is equal to 5x plus 6x log x. Differentiating this again with respect to x. So we get d3y by dx cube. This is equal to differentiation of 5x is 5 plus 6, and here we will use the product rule. First function differentiation of second plus second function into differentiation of first is 1. So what we get is 5 plus xx cancels, we get 6 plus 6 log x. 6 log x. So this is equal to 11 plus 6 log x. We have to find the fourth derivative, fourth order derivative. So differentiate this again with respect to x. We get d4y by dx 4. This is equal to differentiation of 11 being a constant is 0 plus 6 into 1 by x. This is equal to 6 by x. So fourth order derivative of y is 6 by x. Hence proved. Now these two questions you can try yourself. Y is equal to e to the power of minus x cos x. Differentiate both sides with respect to x. What we will get dy by dx is use product rule here and obtain the answer. Differentiate it again and we will get the second order derivative. Similarly in this y is equal to this, we have to prove that the third order derivative is this much. First order derivative will be dy by dx is equal to dy by dx of this 1 by sin x into dy by dx of sin x, that is cos x. So we have cos x by sin x. So first order derivative is cotangent x, second order derivative will be minus cosecant square x, and differentiate this again with respect to x, we will get the third order derivative. You can try this on similar lines. The next question is, we are given y is equal to this much and we have to prove this question. Y is given to be sine inverse x whole square and we have to prove this. So what we do is we differentiate this with respect to x. So y1, first derivative of y is y1, and this must be equal to 2 sine inverse x into d by dx of sine inverse x. Sine inverse x. Differential of this is 2 sine inverse x into d by dx of inner function, that is sine inverse x. So this is equal to 2 sine inverse x into d by dx of sine inverse x is 1 over under the root 1 minus x square. Cross multiply these two equations. We get 1 minus x square into y1 is equal to 2 sine inverse x. This has been taken to the other side. So this is this much. Now we have to prove an equation in which y, y1, y2 are involved. Do is we replace this by y. What we do is square both sides. 1 minus x square into y1 square. And this will be 4 sine inverse x whole square. Now we replace this by y. So what we get is 1 minus x square into y1 square is equal to 4y. Now differentiate it once again to obtain y2. So what we do is differentiating this again with respect to x. Differentiating again with respect to x. What we get is first function into differential of second, that is 2y1. Differential of this is 2y1 into differential of inner function, that is y1. Differential of y1 is y2. So first function differentiation of this plus second function into differential of first is minus 2x. This must be equal to 4. Differential of y is y1. So what we see is this 2 cancels throughout. This 2 cancels throughout. And y1 also cancels. This also cancels. y1, y1 and y1. And we are left with 1 minus x square into y2 minus x y1. This must be equal to 2. Hence proved. This 2 can be taken to the other side. This is this, this is this, this is this. Hence proved. Now next question is, we are given y is equal to e tan inverse x. Y is equal to e tan inverse x, and we have to prove this relation. So what we do is we differentiate both sides of this equation with respect to x. What we get is y1 is equal to e to the power of tan inverse x. Differential of e to the power of x is e to the power of x into differential of inner function, that is d by dx of tan inverse x. And this implies y1 is equal to e to the power of tan inverse x into d by dx. So tan inverse x is 1 over 1 plus x square. Differential of tan inverse x is this much. Cross multiply, we get 1 plus x square into y1 is equal to e to the power of tan inverse x. And this can be written as 1 plus x square into y1 is equal to e to the power of tan inverse x is y. Now differentiate this with respect to x. So what we get is differentiate both sides with respect to x. What we get is first function into differentiation of second. Differential of y1 is y2 plus second function into differential of first. Differential of first, this is 0, and differential of this is 2x. This must be equal to differential of y is y1. So what we get is 1 plus x square into y2 plus 2x. y1 is common. This term can be taken to this side, and what we get is y1 into 2x minus 1. y1 into 2x minus This must be equal to 0, hence these two questions you can try on similar lines. Here y is given to be tan inverse x. Differentiate both sides of this equation with respect to x. We will get y1 is equal to 1 over 1 plus x square. Cross multiply and differentiate again to get this. Similarly for this, differentiate this, cross multiply and differentiate again. You will arrive at this result. You can try these two questions on similar lines. Now next is logarithmic differentiation, and we are given this function and we have to prove that its second order derivative is 0. Now we can differentiate this directly with respect to x and then find dy by dx and then d2y by dx square, or a better method will be take log both sides, because then we will eliminate the product rule and the chain rule. Take log both sides. What we get is log of x to the power of L y to the power of m. This is equal to log of x plus y to the power of L plus m. So this is equal to, now this will be log of x to the power of L plus log of y to the power of m. This is log of x to the power of L plus log of y to the power of m is equal to, use the power rule. This will be L plus m into log of x plus y, and this will be L log x plus m log y is equal to L plus m into log of x plus y. You can write this step directly from here. You can directly write this will be log x to the power of L plus log f y to the power of m. So this will be L log x plus m log y. L log x plus m log y is equal to L plus m log x plus y. You can directly write this. Differentiating both sides with respect to x. So what we get is L into 1 by x plus m into differential of log y is 1 by y into differential of inner function. Differential of inner function will be dy by dx. This is equal to L plus m whole into 1 upon x plus y into differential of inner function is d by dx of x plus y. This will be L by x plus m by y into dy by dx. This is equal to L plus m over x plus y whole into 1 plus dy by dx. Now collect terms having dy by dx on one side. What we get is dy by dx into term involving dy by dx. This is m by y. And term involving dy by dx is L plus m over x plus y, and take this to the other side. This will be minus L plus m over x plus y. This is equal to, now write on this side the terms which do not involve dy by dx. There are two types of terms, dy by dx and which do not involve dy by dx. So this will be L plus m over x plus y. This is the term not involving dy by dx, and from here we will have minus L by x. Now take LCM on both sides. This will be y into x plus y. This will be m into x plus y minus L plus m into y is equal to, LCM here will be x plus y into x, and this will be L plus m into x minus L into x plus y. So this is dy by dx. This cancels with this. And we are left with, what we do is we will open these brackets. What we get is mx plus my minus ly minus my whole divided by y is equal to lx plus mx minus lx minus ly whole divided by x. Now this cancels with this, and this cancels with this, and we are left with dy by dx into mx minus ly over y is equal to mx minus ly over x. This cancels with this, and we get dy by dx is equal to y by x. dy by dx is equal to y by x. So first order derivative is dy by dx is equal to y by x. Now we find the second order derivative. Differentiating both sides of 1 with respect to x. What we get is d2y by dx square is equal to, you can see the side sheet. So this will be denominator square, denominator into differentiation of numerator, that is dy by dx. Gx square, gx into f dash x minus fx into g dash x. G dash x is 1. So this is equal to x into dy by dx. dy by dx from 1 is y by x minus y whole divided by x square. So this cancels and y minus y is 0. So this is 0. Now in this question we are given y is equal to x to the power of x, and we have to find its second order derivative. Now this is in the form variable to the power of variable. So we will use logarithmic differentiation. So take log both sides of this equation. We have log of y is equal to log of x to the power of x. That is log y is equal to x log x. Differentiating both sides with respect to x. We have 1 by y, differentiation of log y is 1 by y into differentiation of inner function, that is dy by dx is equal to, now here we will use product rule, first function into differentiation of second, that is 1 by x, plus second function into differentiation of first, differentiation of x is 1. So we have dy by dx is equal to y into x cancels and we have 1 plus log x, 1 plus log x. Now say this as 1, this as 2. Now to find the second derivative we will differentiate this equation, d2y by dx square is equal to first function into differentiation of second. Differentiation of 1 is 0 and differentiation of log x is 1 by x. 0 plus 1 by x plus 1 plus log x into dy by dx. This is equal to y by x plus 1 plus log x into dy by dx. dy by dx is y into 1 plus log x. This is y into 1 plus log x. So this is equal to y is common, y into 1 by x plus 1 plus log x whole square, and this is equal to x to the power of x into 1 by x plus 1 plus log x whole square. So this is the required second order derivative. And second part is, in second part we have to prove this equation. One method can be, we find d2y by dx square and substitute it in this equation, and substitute dy by dx from here in this equation and simplify, we will get 0. But this method is a bit lengthy if this question is directly asked. So what we do is, we take the question in the form d2y by dx square is this much, which involves y and dy by dx. We do not substitute this in terms of its function. We keep dy by dx as it is and y as it is, because we want a relation between d2y by dx square, dy by dx and y. So let them remain as they are. So what we do is, 3 implies d2y by dx square minus 1 plus log x into dy by dx minus y by x. This must be equal to 0. 3 implies d2y by dx square minus this term 1 plus log x into dy by dx minus y by x. This is equal to 0. Now compare this with this equation. What we see is these two terms are same. Only different is this term and this term. So what we notice, in this term there is no 1 plus log x. So what we do is, we substitute 1 plus log x in terms of dy by dx. So from 2 we have 2 implies 1 plus log x is equal to 1 by y into dy by dx. And substituting in 4, we get 4 implies d2y by dx square minus 1 plus log x is 1 by y into dy by dx into dy by dx. So this must be dy by dx whole square minus y by x is equal to 0. We substitute 1 plus log x is equal to this. So this will be 1 by y into dy by dx. This is 1 by y into dy by dx. 1 by y into dy by dx into dy by dx is this one. So this is the required result, hence proved. Now in this question, we are given x is this much, y is this much. The function is defined in terms of the parameter t, and we have to find the second order derivative of y with respect to x at t equal to pi by 6. So first we find the first order derivative. Dy by dx is equal to dy by dt, because y is a function of t and x is also a function of t. So we will have dx by dt, dy by dt over dx by dt. Now dy by dt is equal to, dy by dt is a into differential of sine cube t will be 3 sine square t into differential of a function, that is dy by dt of sine t, and this is equal to 3a sine square t into differential of sine t is cos t. Differential of sine t is cos t. Say this as 3 and this as 4, and dx by dt is equal to, dx by dt is equal to, a is common and differential of 1 is 0, and differential of this will be minus 3 cos square t into d by dt of cos t, d by dt of cos t, and this is equal to minus 3a into cos square t, minus 3a cos square t into d by dt of cos t is minus sin t. So minus minus will be plus. This is dx by dt. Substituting 4 and 5 in 3. What we get is dy by dx. This is equal to dy by dt. dy by dt is this much. So 3a sin square t cos t whole divided by dx by dt. dx by dt is this much. So this is 3a cos square t into sine of t. Now this 3 cancels with this, a cancels with a, cos t cancels with this, sin t this, and we are left with this is equal to sin t over cos t, that is tangent of t. So dy by dx is tangent t, and we will prefer the notation y1 here. So y1 is this, and we have to find its differentiation with respect to x. So differentiating again with respect to x, what we get is dy1 by dx, and this will be dy1 by dt. This is a function of t and x is a function of t. So what we get is dx by dt. This is equal to dy1 by dt. Now differentiation of y1 with respect to t is, differentiation of tangent t is secant square t whole divided by differentiation of x with respect to t, dx by dt is this much. So this is 3a cos square t from 5, 3a cos square t into sin t, and this is equal to, now cos square t, 1 over cos square t is secant square t. So this will be secant 4t. This will be secant 4t divided by 3a into sine of t, 3a sine t. So this is the second order derivative, and this implies dy1. First order derivative of y1 is second order derivative of y. So we write this as d2y by dx square is equal to secant 4t over 3a sine t, and d2y by dx square at t is equal to pi by 6 is equal to, this is secant 4 pi by 6 divided by 3a sine pi by 6. Pi by 6 is 30 degrees. So secant of 30 degrees will be 1 by cos of 30 degrees. Cos of 30 degrees is root 3 by 2. So this will be 2 by root 3. So this will be 2 by root 3 to the power of 4 whole divided by 3a, and sine of pi by 6. Sine of 30 degrees is 1 by 2. This is 1 by 2. So this is equal to 16. 2 to the power of 4 is 16, and 3 to the power of half to the power of 4 will be 3 square. 3 square, that is 9 over 3a and this will go in the numerator, so this will be this. So this is 32 over 9 3s are 27. 32 by 27, which was the result to be proved. 32 by 27, 32 by 27, hence proved. So what we do is dy by dx is dy by dt over dx by dt. Find dy by dt from here and dx by dt from here. We will get the first order derivative. Denote it by y1, and now the question changes to y1 is equal to tangent of t, and x is a into 1 minus cos cube t, and we have to find the derivative of this with respect to x, derivative of y1 with respect to x. So this will be dy1 by dt over dx by dt. dy1 by dt is this much, and dx by dt we have already obtained it. This was 3a cos square t sin t. So this is the answer. So after obtaining the first order derivative, we redefine the question as this and find the first order derivative. Same method will be applied again. And if we have to find the third order derivative, we will denote this by y2. This by y2, then third order derivative will be dy2 by dx. That is dy2 by dt over dx by dt. Now in this question, we are given x is this much and y is this much. We have to prove d2y by dx square is this much. So what we do is we first obtain the first order derivative of y with respect to x. That is dy by dx. And this is equal to dy by dt over dx by dt, because y is a function of t and x is again a function of t. Now we obtain dy by dt and dx by dt. So dy by dt will be equal to a into differentiation of this. Differentiation of sine is cos t. Differentiation of sine is cos t minus. Here we will use the product rule. So this will be first function into differentiation of second. Differentiation of cos t is minus sine t plus second function, that is cos t, into differentiation of first, that is t is 1. Differentiation of t with respect to t is 1. So this is equal to a into. Now this cos t cancels with cos t. This is cos t, this is minus cos t. And we are left with a into t sine t. This is minus minus plus. So t sine t. We get a t sine t. So we have obtained dy by dt. Now we obtain dx by dt. So this is dx by dt. This is equal to a into differentiation of cos t is minus sine t plus first function t into differentiation of sine t is cos t plus second function, that is sine t into differentiation of first is 1. Now minus sine t cancels with sine t, and we are left with a t cos t. A t cos t. Now say this as 1, this is 2, this is 3, this is 4, and let this be 5. Substituting 4 and 5 in 3. Substitute dx by dt and dy by dt here. We get dy by dx is equal to dy by dt is a t sine t, and dx by dt is a t cos t. So this is equal to tangent of t. and denote this by y1. Now we have to find the second order derivative of y with respect to x. So what we have to find is dy1 by dx. This will be the second order derivative of y with respect to x. So denote this by y1 and find its first order derivative. So this will be dy1 by dt whole divided by dx by dt, and this is equal to dy1 by dt. Differentiation of tangent is secant square t whole divided by dx by dt, and dx by dt is at cos t. This is at cos t, and this is 1 over cos t is secant t. So this will be secant cube t over a. Secant cube t over 80. This was the result to be proved. Now suppose we have to find the third order derivative of this. So what we will do is we will denote this by y2 and find its first order derivative. y2 will be this and x is this, and we have to find its first order derivative. So y3 will be dy2 by dx, and this will be dy2 by dt whole divided by dx by dt, and dy2 by dt. Now we find dy2 by dt. This is equal to 1 by a is common, 1 by a is common, and here we will use the quotient rule. So this will be t square, denominator square, into denominator, into differentiation of this g t square gt into f dash t, that is 3 secant square t into differentiation of inner function, that is secant t is secant t tangent t, minus this is gt square gt into differentiation of this, minus f t into differentiation of gt, that is g dash t. So this will be 1, and this is equal to, now this is secant square t into secant t is secant cube t. We will take secant cube t outside. So this will be 1 by a into secant cube t is common, and we are left with 3t, secant cube t is common, 3t tangent t, 3t tangent t minus secant cube is common minus 1. So this is, so dy2 by dt is this much. dy2 by dt we have obtained, and dx by dt is known from here. Substitute in this and we will get the result. Say this as 6, this as 7. Substituting 5 and 7 and 6, what we get is y3. You can see the side sheet. y3 will be dy2 by dx. dy2 by dx is 1 by a into secant cube t whole into 3t tangent t minus 1 whole divided by t square. This divided by dx by dt. dx by dt is at cos t, is at cos t, at cos t, and this is equal to 1 by a square into, we will have, this will be t cube, and 1 upon cos is secant. So this will be secant to the power of 4t into 3t tangent t minus 1. We have written a into a is a square, t square into t is t cube, cos of t is 1 over cos t is secant t, so this is secant 4t, and this term, this is the value of the third order derivative. These two questions you can try yourself. dy by dx will be dy by d theta over dx by d theta. You will get the first order derivative. Then we have to find dy1 by dx. It will be dy1 by d theta over dx by d theta, and you will get the second order derivative. Similarly, in this case, you can try these two questions yourself.